Hi everybody, my name is Bennett Gildy, and for my final physics project I decided to do destructive interference in noise cancelling headphones. So first, what are sound waves? Sound waves are mechanical vibrations that travel through air, water, or solids by causing molecules to vibrate back and forth, which will then transfer energy without moving any matter. Some important vocabulary to note. First we have our amplitude. It's measured in pascals, and it is the total maximum displacement or distance moved by a point on a wave measured from the equilibrium position of that sound wave. We have frequency, which is measured in hertz, and that's the number of waves that pass through a given point over a certain time period. And finally, we have our angular frequency, which is measured in radians per second, which indicates the angular speed of a given point on a sound wave, typically represented as omega. Some other important vocabulary to note is our crest, which is the top pressure point of the wave, our trough, which is the bottom pressure point of the wave, and wave superposition. That's measured in pascals. Now, oftentimes, your wave superposition varies on the units for amplitude. So in this case, we're using pascals for our amplitude, so we're going to use pascals for our wave superposition. So wave superposition is when two or more waves travel together through the same medium at the same time. They pass through each other without influencing one another, which then produces a combined wave. Now we can see in this diagram we have our crest, which is the top of the wave, and our trough, which is the bottom. Moving on to destructive interference. Destructive interference is a wave displacement of one wave is positive while the other wave is negative, so the net sum of the wave superposition should be 0 pascals. Now we can see in this diagram here that this red wave indicates our destructive interference, and this blue wave indicates our constructive interference. Now we can see around the 4 interval mark that we can see that the red wave, the trough, is overlining with the crest of the constructive wave, which will cause destructive interference. Now, step 1, the microphones detect incoming noises. When we're talking about noise canceling headphones, these microphones are located on the middle portion of the speaker. Some sound waves include engine hum, airplane noise, and dog barking. Right. And then step 2 is headphones will then analyze the wave. The internal process must determine the amplitude, which is the intensity, and the frequency, which is the pitch. Step 3, the system then generates an inverse wave that has the same amplitude, frequency, and 180 degrees out of phase to cancel out the original wave. So we can see in this diagram, right, that we have our microphone here, we have our sound waves created by a headphone speaker, and we have our noise created by external source. And what we see is that with our sound waves created by the headphone speaker is that they're the same, that the troughs of the sound waves created by the headphone speaker are overlapping with the noise created by the crests from the noise created by an external source, which will, when overlap, they'll create destructive interference, which will lead to silence. Some variables and equations. So step 1 is modeling the incoming sound wave. Sound waves can be written as y1 equals a sine omega. Y1 is represents our modeled incoming sound wave. A is equal to the amplitude. Remember that we measure that in pascals. Omega is equivalent to 2 pi f, which is our frequency. Remember, our frequency is measured in hertz, and omega will represent our angular frequency. In step 2, we have to create the canceling wave. So we have y2 equals a sine omega plus pi, which when we talk about pi, our pi is where we are at 180 degrees out of phase. So that will give us our negative, which will create the canceling wave. So y2 represents the canceling wave. Now step 3, we have to add the waves, which is our wave superposition. So it's our y total is equal to y1 plus y2. Now y total equals a sine omega plus a sine omega plus pi. In order for perfect destructive interference, the sum of this equation must equal 0. Moving on to our example problem. We have a teacher is teaching a lesson during class when she sees one of her students with their headphones on. The teacher tries to get her attention, yet because of the noise canceling capability of the headphones, the student is unable to hear. The sound level of the teacher's voice is 0.235 pascals while having a frequency of around 200 hertz. The headphones must produce a sound wave with the same amplitude and frequency, but 180 degrees out of phase with the teacher's voice to achieve destructive interference. Find the amplitude that is required to achieve destructive interference. First, we have to look at our givens. Our sound wave produced is around 0.235 pascals, while we have a frequency of around 200 hertz. So when we go back to our equations, we can see that y1, which represents our incoming sound wave, is equal to A, which is our amplitude, times sine times 2 pi f. So we can rewrite this equation. So our y1 is equal to 0.235 equals our amplitude, which we need to find. So then we have our sine times 2 pi, and our frequency is 200 hertz. So when first thing we have to do is we have to do our sine times 2 pi times 200. When we do that, we get, so let's write out the full thing, equals A times 0.0586. And now we need to solve for the amplitude. So we're going to divide that 0.0586 by itself, and when we do one side, we have to do the other, which we are left with 4 pascals. And now when we go over here, that's our amplitude for the first one. So equals 4 pascals. But now we need to do our superposition. So our superposition is our y total, which is equal to y1 plus y2. Our y2 represents the destructive interference wave that's created by the microphone. We'll write that down. Now going through these steps, I love to write everything down because it keeps me organized and it shows all your work. So we have our destructive interference. So our y1 is equivalent to y total. And now we need to know that our y total, when we're looking for destructive interference, it always must be 0. So we can say that. We can say, okay, 0 equals 0.235 plus y2. So then you're going to subtract 0.235 from both sides. We can see that y2 is equivalent to negative 0.235 pascals. This represents our destructive interference. And finally, here is my works cited page. Thank you for taking the time to listen to my presentation, and I hope you have a great day.